Let me preface this video with I'm not an expert on Feynman diagrams, but I think I know what IB wants us to know. So anyway, so basically a Feynman diagram is a diagram that shows particle interactions. So for example, here's a neutron decaying into a proton, and an electron and an anti-electron neutrino. Okay. This, by the way, this is the same exact diagram, except here they show the quarks, which I thought was kind of neat. Notice that position is to the right and time is this way. So if we look in time, we have a neutron to begin with, right? And then at some point we have a proton and a W minus. And then at some later point in time, we have, like here, right? Here we have a proton and a W minus. Here we've got a proton, an electron minus, a regular electron, right? And an anti-electron neutrino. So there's some sense, and the position is sort of a rough thing, right? We're not really, nobody's measuring these angles. Okay, these little dotted lines, those are the exchange particles. Okay, so if it's a neutral thing on this side, it'll be a Z naught. If it's a positively charged side over here, it'll be a W plus. And if it's negatively charged, it'll be a W minus. So that's what you'll see in these weak interactions, right? If it's a electron repelling an electron, that'll be a photon, right? And then for IB, they want us to use pions as the mediators of the strong nuclear force, okay? And you'll see those. We'll maybe look at some of those in a sec here, okay? So those are the exchange particles. They're either a dotted line or a wavy line, right? And then the matter particles, if they're matter particles, they have an arrow that's forward in time. So notice that this neutron is a matter particle. So it goes forward in time. Proton is matter, forward in time. The electron is a matter particle, so it goes forward in time. But the anti-electron neutrino is an antimatter particle. Okay, so it goes backwards in time. Or it's shown going backwards in time. Of course, it still goes forward in time. Okay. But the arrows, its time arrow is reversed to indicate that it's an antimatter particle. And then if you look at these vertices, there's a vertex, there's a vertex, right? These things obey conservation laws. So for example, here we have no charge, here we have positive and negative, so therefore there's no charge in, no charge out, right? Here we have negative into this vertex, right? And we have zero charge because it's a neutrino, right? And then negative charge going this way. So all these vertices, they obey conservation laws. They'll obey strangeness and baryon number and all those things. Okay, let's take a look at a couple reactions here, or a couple decays. This is a mu minus, a regular muon decay, right? Muons will decay into a muon neutrino, and then it's possible for them to turn into an electron and an anti-electron neutrino, okay? So again, time is this way. This is time. This is position, x, right, for both of these. By the way, those axes can be reversed. So sometimes position goes this way and time goes that way. It doesn't really matter. You'll figure it out quickly if they're reversing the axes. And then notice that this is a matter particle, so it goes forward in time. Okay, this is a matter particle, so it's shown going forward in time, right? The anti-electron neutrino goes backwards. It's shown going backwards in time. All these things, of course, move forward in time. Okay, here is a anti-muon decay. Notice that the anti-muon is shown going backwards in time with its time arrow reversed, right? The time arrow of the anti-mu neutrino is also shown backwards in time, right? Then this can decay into a anti-muon neutrino and a anti-electron or a positron, right? Notice that these time arrows are reversed for these, and then notice that the only matter particle here on this whole page, on this whole side, is this electron neutrino. It's a regular electron neutrino, okay? Notice that this is a positive. There's positive stuff over here, right? And so the positive charge here is carried by the W plus, goes to the positron here, right? So in this case, notice we have a W minus, Okay, the W minus is because this is a negatively charged thing over here, right? So if it's a positively charged branch over here, whatever you call this, right, you'll use a W plus. And if it's neutral, by the way, if these things are neutral, then it'll be a Z naught. Okay, you'll see that. All right. I don't know if there's anything else to say about these.